For this example, we're looking at a simply supported beam. It has a transverse load of 20 kips acting midway between A and C. At point C, we have an actually directed load, but it's offset here by 1 foot. What we want to do is, knowing that loading on the beam, what are the shear force and the bending moment diagrams for that beam? So we're going to do the same thing we've done for all other problems. We're going to look for our external reactions first. So our external reactions, we're going to get that from equilibrium. So the reactions we have over here on the left side is AY. I guess I should say right from the word go that X is going to be positive to the right and Y is up. So the roller just has a Y component of support. B has both a Y and an X, like this. We have the external transverse load of 20 kips there at what I will call point D. And here at C, what I'm going to do is recognize the fact that I can move that 20 kip force anywhere I want to, provided that I carry along the appropriate couple that makes it equivalent to what it was before. In other words, I'm going to move that force completely down here to point C. So that's going to be 20 kips, provided that I put the couple here of 20 times 1. The distance I'm moving it down is 1 foot. So this is going to be a couple there, which is 20 kip feet. So whenever I sum my moments about point A, I have the 20 kip force. It has a moment arm of 5. It's going to have a negative SIGN sign. I've got the 20 kip foot couple there at C, and I have the BY, which has a moment arm of 15 feet. And it's also, or it will have a plus sign. So together those add up to a 0 for equilibrium. The reaction force at B, that's going to be 16 third kips. If I sum forces in Y, I got AY, BY, and minus 20, the applied 20 kip transverse load. And so from that, for AY, I get that AY is equal to 44 thirds kips. So now let's do our shear force bending moment diagrams. For shear force, I look over at the left hand side, and what I have there is that V at 0 is equal to our AY. Again, the sign convention for shear force on the left face is positive up, and we drew AY up, so I put a plus sign there. So this ends up being 44 thirds. The shear force at 5 feet, a little bit to the left of there, is what the shear force is on the left side, plus a 0, since there's no distribute load happening between A and D. So this simply is 44 thirds, I'm sorry. There's going to be a jump there at D, so it's going to be what it was at 5 minus plus the minus 20. So that's going to give us the minus 16 thirds kips. And then V at the right side at 15, that's what it is at 5 plus there's no change along the way because there's no distributed load, so that's still at minus 16 thirds. So how does this look? Well, we are at 44 thirds throughout the first 5 feet. So this is 44 thirds. And then there's this drop of 20, which takes us down to minus 16 thirds all the way the rest of the way across. So that's how the shear force looks. Bending moment. So the bending moment, we know, since the left end is free, and that's the way we drew our FBD at the beginning, there is no bending moment there on the left hand side. The bending moment at 5 is equal to the bending moment on the left face plus the integral from 0 to 5 of v of x dx. Again, there's no bending moment on the left hand side. The area under that curve is going to be 44 thirds times 5, whatever that ends up being. And then we have the bending moment then at 10 minus. I need to make a distinction between 10 minus and 10 plus because that's where the couple is applied, is equal to m5 plus this couple, which is going to be the plus couple, but means that the sign conventions are such on concentrated couples of it being a jump down, it's going to be the minus 20 as that. So this is going to be 44 thirds times 5 minus 20, whatever that ends up being. And then over on the right hand side at 15, it's going to be the bending moment I think I erred there. I was trying to work too fast here, and I sort of lost track here. What I need to say here is that m 10 minus is equal to m5 plus the integral from 5 to 10 of v of x dx. Finally, I'm going to get this right. This is 44 thirds times 5 plus the integral of that one, which is going to be minus 16 thirds, 5. And then this is where the jump comes in. I'm not quite sure what I was doing there. Means we have the concentrated couple there at x equal to 10. We have the minus 20 there. So whatever this works out to be, you've got that. And then the bending moment on the right face at 15 should be the bending moment at 10 plus with the integral from 10 to 15 of v of x dx. And this amount here is going to be that amount of minus 16 over 3 times 5. So whatever that ends up being, we know what the answer is. It's a 0. You can check our arithmetic here, but we know it has to be a 0 because the right end boundary condition is one of 0 moment, the pin joint. So what we have then is we can make the sketch of m without having our numbers. We know the m starts out x equal to 0 at 0. It's going to be going with a positive slope because v is positive. We know then it goes down at a negative slope, but not nearly as large in magnitude as the positive slope is. And then there's a jump downward of 20. And then at the same slope, try to make this slope the same as before. So let me try that again. It's going to be something like this. So this amount here is that jump at 20 down. I know it starts out at a 0, it ends up at a 0. I know between 0 and 5 it's a large positive slope. Between 5 and 10 it's a negative slope, but not quite as large as the positive one is. There's a jump downward there at C, and then ends up as a 0 there on the right side. So this problem is just like all the rest, with a slight complication that we begin with a physical problem where we actually had an axial load which was offset from the axis of the beam. That's going to give us an axial reaction, Bx, which we didn't solve for, but if we would have seen that it would have been carrying an axial load. But the important thing is it puts a couple there at C. If I simply use the idea of the equivalent force couple system, I slide that 20 kip force down to C, I need to put a couple on there of 20 times that distance of 1 foot. But once I had that, I solve for my reactions. I go through the process of doing my shear force through this integration and any jumps, the bending moment through integration and any jumps, and that's what we end up with.